Hello, everyone. Welcome back to lecture 4 of this thermodynamics module. Today's lecture, we are going to talk about phase equilibrium and thermodynamic models. Just a quick recap of lecture 3. So lecture 3, we really talked to you about how to use thermodynamic relations and then trying to calculate the changes in entropy, enthalpy, and internal energy between two different states. As long as you know the CP and PVT relationship, you can actually plug in and then you can calculate the delta S, delta H, delta U between these two states. And for particularly for ideal gas, we know CP is constant, PV is equal to RT. You plug in, these are the equations that you can simplify from these. Simplify first and then take the integral. These are the answers, right? Now, CP, we mentioned CP is usually constant or sometimes like depends on temperature. So it's going to be a function of temperature or constant. But for PVT relationship, in addition to ideal gas law, PV equal to RT, we talked about different types of EOS for real gases, including virial coefficient, virial equation of state, cubic equation of state, including Van der Waals equation, Radrich-Kwong equation. And then for all these equations, right, we talked about the compressibility factor Z is equal to PV equal to divided by RT. And then for all these equations, if you go to the P equal to 0 limit of V goes to V infinity limit, you will actually recover the PV equal to RT, which is the ideal gas law. So that's why we say, right, for gases at low pressure or extremely high temperature, usually they behave like ideal gas, okay? And then we talked about how to use generalized correlation to calculate Z factor, right? And then this Z we said, right, it's actually correlating between, quantifying the deviation from the ideal gas behavior for real gas. And that deviation difference in thermodynamic properties is defined as residue property. Residue property is basically the real gas property minus ideal gas property, okay? So that's our lecture 3. Now in today's lecture, we are going to switch gear a little bit. We are going to talk about phase equilibrium and then how to analyze these phase equilibrium using thermodynamic models, okay? So by the end of this lecture, you should understand what do we mean by phase equilibrium and also how to use these models to understand the chemical mixing and also relevant to separations. And we will first talk about phase rule, and then we will show you phase diagram, and then use the Raoult's law to analyze this phase equilibrium. And we will talk about ideal and non-ideal mixtures, including gas mixture or liquid solution. And then we will introduce you fugacity, activity coefficient, and then finally talk about Gibbs free energy, excess Gibbs free energy, and using these equation to analyze the vapor liquid equilibrium of a particular species, okay? All right, right ink. Now, phase changes, right? Now here, when we are talking about phase changes, we are really talking about the physical, the change in physical states, okay? Not involving chemical reactions. So we actually change from either a gas state to a liquid state or vapor. Gas is or sometimes called vapor, right? Vapor converting to liquid. So now imagine you have like the piston, right? And then your system is a collection of gas molecule, okay? But now what you are going to do, and let's say this is your real gas, okay? Now I'm asking what's going to happen if you compress a real gas, okay? So basically, if you imagine this real gas in a PT diagram, so y-axis is your pressure, x-axis is temperature. Let's say you start from a vapor state, like somewhere here, right? Okay, so below TC, below PC, and it's behaving like a vapor here. Let's say this is your P1, okay? Now, when you are compressing while holding temperature constant, let's say, so basically you are moving up in this line. So what you are going to hit, basically, you're compressing these gas molecule, and then by bringing these gas together, and then by if they reach a reach a certain point or hit this liquid line, basically you will have, a droplet coming out. So imagine a water vapor, right? You compress, 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 and then you will have water droplet coming out, right? So basically they condense into liquid water. Okay, and then if you keep compressing, then all the residual gas vapor or water vapor will continuously condense into liquid. And then until you finish condensing all of them into liquid, right? Then your pressure will start to rise again. So when you go from P1 to this equilibrium line, so vapor liquid equilibrium line, the phase transition will occur between vapor into liquid droplet, right? This phase transition will continue until all the gas vapor or all the water vapor or the vapor molecules, all of them condense into liquid, right? Then you can compress further, and then the pressure will rise again until you reach a critical pressure, okay? PC. And then when we talk about critical point, then we are talking about really the temperatures above TC, pressures above PC, then you are actually behaving like a supercritical fluid. Basically it has both liquid and gas properties, okay? All right, so this is the phase transition or phase change that we are going to focus on today. So in this particular case, we are looking at the vapor to liquid transition, okay? So it's a phase change. Now, by phase, what we are really talking about is, by definition, a phase is a homogeneous region of matter. So in the previous case, right here is a gas phase or gas or vapor phase. So everything is vapor, right? Now here, when you have the first liquid water droplet appears, then you have two phases. One is the gas phase here in purple, and then the liquid phase in blue, right? And then you keep going until all the gas vapor disappears. So now you have only one phase, which is a liquid phase, okay? So this phase is really a homogeneous region of matter, okay? Now, if you are talking about a PT diagram for pure substance, usually you will have four distinct phases. The first is solid. Solid is usually at lower temperature, higher pressure, okay? And then you have liquid. Liquid is higher temperature than solid, right? So you go through this melting process, right? And then vapor is basically you go from liquid to vapor by boiling, right? And then you go up, and then you will go up to the supercritical fluid region, which is above TC and above PC, okay? So there are four phases, okay? Or four states. And then you have three equilibrium curves. All these are called phase coexistence curve. Specifically, we have a vaporization curve or vapor liquid equilibrium curve. We have a fusion curve. Fusion curve is basically a solid liquid equilibrium curve. We talked about the melting or crystallization, right? And then we also have a sublimation curve, directly go from solid to vapor. It's basically a solid vapor equilibrium curve. So these are three equilibrium curves, right? 1, 2, 3. And then we have 4 points, right? Any point on this fusion curve is going to be a melting point, right? You are going from solid to liquid, you are melting solid into liquid. And then on any point on this vaporization point, vaporization curve is called boiling point, right? So when you heat the liquid up from like room temperature all the way up to 100 degrees C for liquid water, then liquid water will start to boil and enter to the vapor phase, right? So this is the boiling point. And then we also have a triple point. Triple point is basically you have like solid, liquid, and vapor coexist on this particular point. So you have three phases at this particular temperature and pressure. Okay, and then finally is this critical point. Critical point is basically TC and PC for a particular substance. And then in previous lecture, we already know, right, for a specific species, TC and PC is usually fixed, right? So you can look those values up. And also this triple point for a particular species, you can also look up the triple point. So these 2 points are fixed, right? But for boiling point and melting point, it will actually depends on your pressure of the system, right? When the pressure increases, usually the melting point increases and also the boiling point increases, okay? All right, so those are the typical phase diagram, how you understand the PT diagram for phase changes, okay? And then you can imagine you are heating ice under ambient condition. Let's say 1 atmosphere, you will go through ice, which is a solid, and then goes to liquid once ice all melt. And then the liquid will hit boiling point at 100 degrees C until they vaporize all the way into water vapor, okay? All right, so now you may wonder, right, what determines the phase, right? So how do we know at a particular temperature and pressure it will be either gas or liquid state? How do we know, right? So now we actually have a phase rule. Phase rule is basically giving you an equation to determine the degree of freedom, or in other words, number of intensive properties required to define a thermodynamic state, okay? So F is degree of freedom, and then is equal to 2 minus pi plus n, okay? Pi is the number of phases in your system. If it's a pure gas phase, then we are the number of phases 1 here, right? If you have a mixture, number of phases is 2, right? Gas and vapor, gas and liquid. And then if it's purely liquid, then phase is again coming back to 1, okay? And then the number of chemical species is your number n here, right? If we are talking about a pure species, then the number of species in this particular case is just equal to 1, okay? All right, so now let's quickly understand on this PT diagram, right? How many intensive variables that we need to know to specify or to define a thermodynamic state. So example 1, we are looking at one phase, one component, right? We want to ask how many thermodynamic properties that we need to know to actually locate this particular system onto this PT diagram. So if it's one phase, one component, right? So pi is equal to 1, n is equal to 1, right? Then free F, if you plug in, then you will know F has to be equal to 2, right? So that means you need to know 2 intensive thermodynamic properties so that you can actually define a state. So really trying to figure out the system is either in the solid state, liquid state, or vapor state, okay? So if you imagine, right, if you only know temperature, let's say you only know one intensive variable or intensive property, which is temperature, right? It could be here. So you draw a line like that, then your pressure, let's say we didn't specify, then your system will be either in a vapor state or a liquid state, right? So you don't really define a specific state for this particular system yet. So then you will need a second variable, which is your pressure, so that you can actually, with 100% confidence saying that, oh, at this particular pressure and also the same temperature, is going to be in a vapor state. Let's say if this pressure is below this equilibrium line. But if it's above this equilibrium line, then you will be in the liquid state, okay? So that's why in this particular case, right, if we are dealing with one phase, one component, right, one phase, one pure substance, one component, you actually need to know both temperature and pressure to really say that this system is either in the vapor state or in the liquid state, okay? So degree of freedom is equal to 2. If two intensive properties are fixed, thermodynamic state of the system is fixed. Okay. All right. Now, if we have another example, now let's say you want to, we already tell you this system is actually on the vapor liquid equilibrium line of one component, right? One component n is equal to 1. And then we already, at the beginning, we already tell you, right? We know this system is sitting on this line, is either experiencing vaporization or condensation, okay? But we know it's on this line. Then we want to ask, right? If we say it's on this vapor liquid equilibrium line, then in addition, how many intensive variables that we need to know to actually define the state or to locate this particular system on this PT diagram. Okay, so two phases, one component. So pi is equal to 2, n is equal to 1. F, you plug in, you will calculate F is equal to 1. So here, if you are on this line, then you really just need to know one intensive property so that you can actually fix or define the thermodynamic state. So let's say again, the temperature is this, because you know it's on this line, so you can actually just like draw a horizontal line intersecting with this line, and then basically this is the state that you are looking for, okay? So if it's on this line, then you know if your temperature is given, then your pressure is going to be fixed along the vaporization curve. So in this particular case, you only, when you analyze a system going through a vapor liquid equilibrium or reach a vapor liquid equilibrium, then you really only need to know temperature or pressure to actually define where it is on this PT diagram, okay? All right, and then more specifically, we're not going to go through the derivation, but this PT on this PT diagram, these equilibrium curve, right? You can see they have a slope, right? And then that slope, you can actually calculate it based on the enthalpy change associated with this phase transition from going from alpha phase to beta phase, divided by temperature at which the phase transition is occurring, and then delta V is the volume change by going from alpha phase to beta phase, right? So dP dt is basically the slope at any instant point, and the slope can be calculated from delta H divided by T delta V, okay? Again, we are not going to go through, but if you're interested, you can read the additional slide to figure out why we have this particular slope. And for ice is really, for water is really unique, right? Because for most other common species, right, the slope of this, your solid liquid line is a steep positive slope line. But for ice to liquid, right, this slope is actually steep but negative. That's because ice has a lower density than liquid water. So when you are crystallizing into ice, you are actually expanding in volume. So this delta V going from ice to water is actually negative. So that's why you will have a negative slope. Okay. All right, but anyway, coming back to this phase rule, right? If you are sitting on this line, or if you are dealing with a vapor liquid equilibrium of a system, you just need to specify one intensive thermodynamic property, either temperature or pressure. Okay. All right, so that's the phase change or phase equilibrium for a pure species, right? So N is equal to 1 case. But now how about multi-component system, meaning that we are talking about now a liquid mixture, liquid A mixing with liquid B, or gas mixture, gas A mixing with gas B. And then in this particular case, now the system, we have a multi-component, so your N is going to be greater than 1. Okay. So just a real life example is coffee, right? I drink coffee every day, but what comprises, what components does coffee have? Well, it has water for sure, right? And then it has some caffeine, right? Caffeine is making you energetic, right? And then some people will also put in some sugar, right? At the end, everything dissolve in this liquid, right? So everything become a liquid solution, right? Containing dissolved species and also liquid water. Now we just need to understand, right? How does this adding sugar change the entire property of your coffee, right? Of course, we know putting sugar will make your coffee sweeter, less bitter. But we need to know, right? Adding a small amount of sugar, how much does it change in terms of like the overall properties of coffee? Now that is actually quantified by partial molar property, which we will define in a minute. But first, let's just like get some nomenclature on the same page. Okay, so when we are talking about mixture or liquid solution in this case, we can talk about the solution property or mixture property, right? Usually we use capital M. When we are talking about a mixture, we just use M, okay? Without anything else. So you can talk about volume, internal energy, enthalpy, entropy, Gibbs free energy. And then we also talk about partial molar property. Then we will have a bar on top. So, and when we are talking about partial molar property, it's usually specific to a component, right? So for this, in this example, we are talking about adding sugar. We are trying to understand adding sugar. How does it change the overall property? So here, I will be the partial molar property of sugar. So I should be sugar, right? So sugar bar. And then you can have like VI bar, UI bar, right? HI bar, SI bar, GI bar. And now we can, like for making this mixture, right? We have sugar, pure, liquid, pure, caffeine, pure, and then you mix everything together to form a solution. But if you isolate them apart into their original pure form before mixing, then we can talk about pure properties, right? Pure properties, we just use MRI without a bar on top. So these are molar properties of your pure species, BI, UI, HI, SI, GI. Okay. Now, when we are trying to quantify how the addition of the sugar it will change the overall properties of the coffee, that we need to that is usually quantified by this partial molar properties. So basically, we are trying to understand, right, by adding a small amount of sugar, how much the overall property is going to change by the amount of this sugar that we add in. So definition of your partial molar property is MI bar is equal to partial derivative of NM. NM is the total property of your mixture. So if you say UM is U, so it's going to be N times U. U is the molar internal energy of your mixture times moles give you the total internal energy of the system. right? We are trying to see how this total energy of internal energy is changing with respect to Ni, right? Ni here we are increasing the moles of sugar, right? So partial Ni. But when we are doing this, we are holding everything else constant, right? We are holding temperature, pressure, or we are holding other species, quantity constant. So let's say Nj constant. If you are talking about a binary mixture, then you can use 1 while Y holding molecule 2 constant, right? But if you are talking about multi-component, then 1 and then Nj, J is equal to 2 and 3, okay? So basically, this is like we are trying to quantify, right? How does the total property depends on the addition of a small amount of I species in the mixture, okay? So this actually measures the response of total property Nm to the addition of an infinite small amount of species I to the system at constant temperature, pressure, while holding everything else like all the other species constant, okay? All right, so that's the general form. A special case that we need to focus on is called this Gibbs free energy, right? For the multi-component system, the total Gibbs free energy will be a function of temperature, pressure, and also the moles of the species in the system, right? So this Ng is going to be the total Gibbs free energy of your system. Now we can take a differential form for this. dNg is going to be, again, taking this, taking partial derivative with respect to t, Tp, and then taking this partial derivative with respect to t, holding everything else constant, dt. And then now you take partial derivative with respect to Ni, holding Nj constant. And then here, if it's a binary system, like I said, right, it's going to be 1 to 2, right? So partial N1 holding N2 constant, partial N2 holding N1 constant. But if it's a multi-component system, then you need to go all the way and then sum them up, okay? All right, so if you recall, dg is equal to vdp minus sdt. So basically, this whole thing is your nv, and this whole thing is your minus ns. And then here, right, if you look at this expression, then we are talking about taking a partial derivative with respect to ni holding nj constant, tp constant. Right? If you go back to the previous slide, basically that's the definition of your partial molar property. And here in this particular case is a partial molar Gibbs free energy. Now, because it's so important, we actually give it a special name, partial molar Gibbs free energy. We call it's a chemical potential, okay? Mu I. Mu I is your chemical potential. It's a partial molar Gibbs free energy, okay? So the definition of chemical potential, again, is partial molar Gibbs free energy, partial Ng, partial Ni, holding Tp and J constant. And then if you want, you can actually write it out as Gi bar, right, for a multi-component system. Now, without the revision, I'm going to show you, right, the relationship between molar properties of the mixture and also the partial molar properties is going to be M. M is the mixture molar property is going to be summation Xi Mi, right? Xi is the molar fraction of the species I, and then Mi bar is going to be the partial molar property of that I in the multi-component system, okay? So this equation is can be used to calculate molar property or M of the mixture from partial molar property Mi bar of the species within this multi-component system, okay? If you are interested in why we have this equation, you can look at the additional slides. Now, in addition to this equation is also important. It's called Gibbs-Duhem equation. So basically, if you sum up xi dmi bar, you will actually get 0. Okay, so later we may use this equation for future derivations. But for now, basically, this is the correlation between mixture property with partial molar property, and then the molar fraction, dmi. They actually have like this. They have to fulfill this equation. Okay, at constant temperature, pressure. All right. So that's chemical potential, right? Chemical potential is a partial molar property, called partial molar Gibbs free energy. Okay. So now let's focus on the mixture, right? The mixture can be a gas mixture or can be a liquid mixture, like I mentioned. First thing first, let's start with the simplest mixture, which is ideal gas state mixture. Okay. So in this particular system, basically we have, gas molecule A, gas molecule B, and then let's say the system pressure is small. So the whole system behaves like an ideal gas. The whole mixture behaves like an ideal gas mixture, okay? Now recall for ideal gas law, right? VIG is equal to RT divided by P, okay? And then VIG at given T and P, you will be the same for both pure and mixed gas, right? Because remember, for ideal gas, we are actually assuming, right, the gas molecule have negligible particle volume as compared to the container. So it doesn't matter what your gas identity is, gas A or gas B, they all have the same molar volume, right? So VIG is always going to be equal to RT divided by P, okay? And then if you are talking about like this is like the mixture V, and then if we want to calculate the partial molar volume of species I, then you just plug into the definition for your partial molar property. And then NVIG partial NI holding in J constant. So like I said, VIG, we already know it's NRT divided by P, right? Partial NI. So RT and P are given. So these are constant. So you essentially you're just taking partial derivative N with respect to NI. So, but we are holding in J constant. So this is constant. So N is equal to Ni plus constant. And then when you take the partial derivative, basically it's equal to 1. So it's going to be RT divided by P. Okay. So the partial molar volume is also equal to RT divided by P. But the gas mixture volume is also, molar volume is also equal to RT divided by P. So that means your partial molar volume is equal to the molar volume of the mixture, right? So this is the expression VIG bar TPN VIG pure species, the same. And then ideal gas mixture, the same. All of them is going to be equal to RT divided by P. Okay, so VIIG, we represent like pure ideal gas I. V without I, we are talking about ideal gas mixture, right? This is partial molar volume of I in the mixture, okay? So now you know, right, the partial molar volume is equal to molar volume. Now the system total pressure is going to be equal to N total, T divided by V total. And N total, we know is summation Ni or all sum up, right? The ideal gas mixture comprised of species of equal molar volume, okay? And then the partial pressure of species I is going to be Pi is just equal to Ni RT divided by V total, right? And then you can actually correlate this equation, correlate Pi with total pressure by molar fraction, basically just like you divide this equation by this equation. So Pi divided by P is going to be Ni divided by N total. Ni divided by N total is just the molar fraction of species I in the mixture, right? So partial pressure is equal to molar fraction of species I times total pressure, or molar fraction is just equal to, because molar fraction is equal to Ni divided by N total by definition, right? All right, so that's unique for volume, right? Partial molar volume is equal to molar volume at a given temperature and pressure. Okay, and then from this we can actually correlate partial pressure with molar fraction. Now, but for other thermodynamic properties, this is not true, right? This is actually Gibbs theorem for ideal gas state mixture, right? So this, the statement of this Gibbs theorem is that a partial molar property other than volume, right? In the ideal gas state mixture as system pressure, right? P is equal to corresponding molar property of the species in the pure ideal gas state at the mixing temperature, but a pressure equal to its partial pressure in the mixture. Okay. So now the mathematically, what does this statement mean is that MIIG bar at system temperature, system pressure. So this is the partial molar property of species I in the gas mixture at system temperature, system pressure is just equal to the molar property of the pure species I in the ideal gas state at the same temperature, but a reduced pressure, which is your partial pressure of the species I within this whole mixture. Okay, so this is basically mathematical version of this Gibbs theorem. Okay, so now this is important so that we can actually go back to the equation, right? So we have an equation correlating mixture property with partial molar property, and then we can use Gibbs theorem to convert this partial molar property to pure species molar property, but at a different pressure, right? Pure species molar property, those are usually given, people already measure it out for you so that we can use those to calculate the mixture property. Okay, so that's what we are going to do. All right, so now you know this from Gibbs theorem, and then we recall, right? Mixture property is just equal to the molar fraction times partial molar property. And then if you times n on both sides, so MIG, right? Because we are talking about ideal gas state mixture, so you will have MIG and then T and P, system temperature, system pressure. And then it's going to be summation, right? In total, you move inside, it's going to be NI, MI, bar IG, right? Telling you ideal gas state. But here we are not changing temperature pressure yet. So this is just like rewriting this whole equation, okay? Now we want to replace this with MIIG T, but at PI. So basically this still the same, right? And MIG as system temperature, system pressure is going to be equal to NI IG T, but instead of P, we now have PI, right? So this is just replacing this with this guy into this equation, okay? So it's going to be mixture property equal to pure species property at the same temperature, but a reduced partial pressure, okay? So here, like I mentioned, this is going to be the total property of the ideal gas mixture or the system that we are analyzing. And this total property could be NU, internal energy, enthalpy, entropy, Helmholtz energy, Gibbs free energy, right? And then this MI is going to be the molar property for species I in the pure ideal gas state, right? That's why we have a subscript I here, okay? All right, so now you go from pure species property, calculate the mixture property, okay? And then if we normalize, we can actually just like get rid of this, and then instead of Ni, we use a molar fraction. For gas mixture, usually we use Yi to represent molar fraction. So again, mixture property at a system pressure, system temperature is equal to the summation of molar fraction times the molar property of the pure species I in the ideal gas state at the same temperature, but partial pressure of the species I in the mixture. All right, so this is ideal gas state mixture, and then this is related to pure ideal gas state. Okay, all right. So now we can actually go use this equation to actually calculate, right? What is your U, H, S, A, G of the mixture, okay? So now coming back to ideal gas mixture, right? Ideal gas, like I mentioned, we don't have like any intermolecular interactions, and then the internal energy or enthalpy is only depends on the temperature, right? So H and U are independent of pressure for ideal gas, right? So here you will see, right, as long as their temperature the same, doesn't matter your pressure is different, still you are talking about like the same property, right? I mean same molar property. So in the end, right, your HI, IG, TPI, let's say this is the pure species property, and then at the reduced partial pressure, right? Because this enthalpy doesn't depend on pressure, right? So it's going to be equal to HIIG T, but at a system pressure. And these are all going to be equal to HIIG, ideal gas state enthalpy, right? So basically, this is the specific or molar enthalpy of pure species I at temperature T. As long as your T is fixed, right? This is fixed, and then same thing with this and this, right? Although Pi is smaller than P, but their enthalpy is the same, okay? So now if you do this, right, then you will quickly realize HIG, the mixture enthalpy is just equal to summation Y I HIIG, right? At system temperature, system pressure, okay? And then IG mixture property is going to be equal to molar fraction times UIIG at, again, system pressure, system temperature, okay? Now, the only thing, things are different for entropy and Gibbs free energy, right? For entropy and Gibbs free energy, they actually have some temperature dependence. So in the end, without going through all the derivation, this is the final answer for your SIG mixture property is equal to, molar fraction SIIG at system temperature, system pressure, but you need to minus R times summation Yi, natural log Yi, okay? And same thing for GI, GTB is going to be the pure species property at system temperature, system pressure. But in order to account for that partial pressure difference PI, the difference between P and PI, you actually need to have some deviation, right? So the deviation is going to be plus RT summation Yi, natural log Yi, okay? Now, if you are interested in how we get these equations, you can read the additional slides, but this is how you calculate the mixture and entropy mixture Gibbs free energy, okay? So now we know the mixture property, we know the summation of pure species property, right? And then the pure species is basically before mixing them up, right? So you go from your initial state, which are pure species, and then go to the final state, which is your mixture state, right? And then we want to ask, what is the change in entropy, Gibbs free energy due to this mixing process? So you can do that in a later slide. I will show you. All right. So that's ideal gas mixture, right? We can also, by analogy, we can also do some ideal solution, right? So ideal solution is basically, more specifically, it's going to be a liquid solution, right? So for this ideal solution model, we are going to use this to calculate thermodynamic properties of ideal liquid solution. And the ideal solution is defined as solutions comprised of species of equal molar volume, equal molecular volume, in which all molecular interactions are the same. So this is in analogy to ideal gas, right? And then similarly, we can obtain SI ID. ID means ideal solution. Okay, ideal gas is IG, right? So this S is for the mixture, and then these molar fraction times pure species S, and then you have some extra term for entropy, right? Minus R summation XI natural log XI. Same for G, ideal solution is going to be summation Xi Gi plus RT, summation Xi natural log Xi. And then chemical potential of the species in the ideal solution is also going to be Gi plus RT natural log Xi, okay? And then VID is summation Xi VI, right? HID is summation Xi HI, UID is summation Xi UI, right? So this, again, the derivation are pretty much like the same, right? Now this equation we will need to use later, so keep an eye on this, okay? Now, like I mentioned, we know the mixture entropy. We know the starting pure species state before mixing them up, right? The change between the mixture and the pure species state is called the change due to mixing, right? So you can actually calculate the change of mixing. By the way, to differentiate between gas and liquid, we use liquid Xi for molar fraction in liquid solution, Yi in gas mixture, okay? Now, speaking of the change of due to mixing, right? So imagine first we focus on ideal gas, okay? So let's imagine you have gas A at system temperature, system pressure, TP. And then you have gas B, also same temperature, same pressure, and you have a separator between these two. And then what you do is that you quickly remove this separator, and then the gas A and gas B will form a gas mixture, right? And then at the same temperature, pressure. You can also imagine this is a solution. We are talking about pure liquid A and B, and then making A plus B liquid solution, okay? All right, so now what we want to calculate is the delta H due to mixing, right? So the change of in enthalpy due to mixing. So let's imagine we are going to base on 1 mole or 1 mole of mass. Okay, so let's say you go from 0.5 mole A, 0.5 mole B, you make a 1 mole of mixture. Okay, so what you do, delta H is going to be HIG. So the mixture final enthalpy minus initial pure enthalpy. Initial enthalpy, which is in the pure species A, pure species B state, right? So we already know this is the mixture property, and then minus summation YI is basically your initial enthalpy. And then this delta H is going to be the change in enthalpy due to mixing, right? So we already know for mixture, HIG is equal to this, right? So the change due to mixing in enthalpy is just 0, right? Same thing with your internal energy. You don't have any change in internal energy due to mixing, but different stories for entropy, right? So entropy, delta S is going to be mixture minus initial pure state, which is going to be YI So basically you move this to the other side, and then you will quickly realize this is going to be minus R summation YI natural log YI. And then we know Yi is a molar fraction, so Yi is a value between 0 and 1. So natural log Yi is going to be negative, 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 positive, right? So delta S mix is always positive, as you can see from this equation. So how to understand this is that usually entropy favors mixing, right? So when you are mixing A and B up, right, you are going from like you are adopting more conformational states, possible conformations. So your system is more random. If your system is more random, then your entropy is going to increase, right? And then when entropy is increasing, usually you are decreasing in Gibbs free energy, okay? So usually entropy favors mixing, okay? And then GIG, you can do the same thing. Delta G mix is going to be this minus this is going to be, RT summation YI natural log YI. Again, this is going to be a negative value, and then overall delta G mix is going to be a negative value. So mixing is usually for gas mixture is usually entropy. Gibbs free energy decreasing process. Okay, so when you are mixing them, you are driving up the entropy, and then because delta G is equal to VDP minus SDT, so your S is increasing, then your G is decreasing. Your delta G is going to be negative. Okay. All right, so now we understand the mixing process, okay? So then we can actually talk about the phase equilibrium of this mixture, right? So let's say you have, let's talk about the phase equilibrium of a closed system with two phases, okay? And then here, two phases, one phase, we can say it's an alpha phase, and then the other phase is a beta phase. So basically here you are looking at a closed chamber where you have liquid on the bottom and then vapor on the top, right? Let's say vapor is your alpha phase, and then liquid is your beta phase, right? And then you will have an interface between liquid and vapor when these two phases coexist, right? So this is the vapor liquid equilibrium at system temperature, system pressure. So both vapor phase and liquid phase will have the same temperature, same pressure, okay? Now, within this alpha phase, right, you can have like two species. You can have like, water and ethanol, both in liquid phases and also in vapor phases, right? So those are going to be multi-components. But at least we have like multi-phases here, okay? All right, so now for a multi-phase equilibrium at constant temperature and pressure, the criteria for phase equilibrium to achieve or to occur is that your chemical potential of your species I in the alpha phase has to be equal to the chemical potential of your species I in the beta phase is equal to the chemical potential of your species I in the pi phase. So at phase equilibrium, T, temperature, pressure, and chemical potential of component I is the same in all phases. You can kind of imagine this chemical potential is driving the component from one phase to the other. When the chemical potential in all phases are equal, then they stop moving between phases, right? So then your phase reach equilibrium, okay? And then again, you can have I equal to 1 or 2 or 3, right? All the way up. But as long as you have chemical potential difference of a particular species in different phases, then your phase is not in the equilibrium state. only when in all phases, right, the chemical potential of a species I is like for every single species within the mixture, you reach equilibrium. Okay, so this is the criteria for you to have phase equilibrium. And then if you are interested in how to derive this, you can actually read the additional slides. Okay, but this is the phase equilibrium criteria, chemical potential being the same. All right, now you can actually use this to analyze liquid vapor equilibrium of ideal mixture. Okay, so let's say you have a binary mixture and you have two, you have a multi-component mixture and then you have two phases. And the phase we are talking about is liquid vapor. Okay. And then recall at liquid vapor phase equilibrium at system temperature pressure, your chemical potential has to be the same. So mu I V, V is in the vapor phase, is going to be equal to mu I L, L is in the liquid phase, right? I again can be 1, 2, 3, all the way up to N. And then from previous slide, remember for chemical potential, I told you to keep an eye on that equation. So mu IV, since it's in the vapor phase, ideal gas mixture, mu IV is GIIG plus RT natural log YI, right? So we already give you that equation in the mixture slide. And then mu IL is GIL plus RT natural log XI, right? And then you plug in and then basically GIG, GIL, these are molar energy for pure species I at T and system pressure. This is in the gas form, this is in the liquid form, okay? And then if we skip a lot of derivations, so this Gibbs free energy in the liquid, Gibbs free energy in the gas is actually related to saturation pressure. Okay, so basically the vapor pressure, PI saturation. So I'm not going to derive that, but basically this gives rise, the difference between these two give rise to this PI saturation. And then if you plug in and you move things around, right, then you will have like natural log yi, xi still in the equation. So in the end, if you move to the other side, natural log yi minus natural log xi is going to be natural log yi divided by xi. And then in the end, it's going to be natural log PI saturation divided by system pressure. Okay, so if you are interested in how to reach this equation, see the additional slide. Okay, and then so from this you can rearrange the equation. So essentially, YIP is equal to XI PI saturation. Okay, so I is equal to 1, 2, all the way up to N, right? And this equation is derived from this equation. So basically this equation applies to the liquid vapor phase equilibrium of ideal mixtures and solutions. Okay, so so here this is like an equation correlating the molar fraction of species I in the solution, molar fraction of species I in the gas mixture, and then the saturation pressure of species I, and then the system pressure in one equation. Okay, and then these are all in the ideal gas, in the ideal mixture states. Okay, now this particular equation, right? In this equation, PI saturation is basically the saturated vapor pressure of pure species I at system temperature, right? So here we know like PI saturation is just equal to a function of T. And then you can actually use Antonian equation, for example, to calculate PI saturation as long as you know T, right? So PI lateral log PI saturation is equal to some constant minus some constant divided by temperature plus CI. Now this ABC values, it's species dependent. We actually have a table tabulated these values. So as long as you know these constants, if you know the temperature, you can actually calculate PI saturation, right? System pressure, we can give you. And then if you know the XI, you can actually simply calculate YI, okay? So that's the whole whole power of that equation. And this equation is actually called Raoult's law for ideal mixture. Okay. Now, you can use this Raoult's law to analyze liquid vapor equilibrium of binary mixture, for example. Now, let's say for binary mixture, right, we are talking about liquid vapor equilibrium. So you have two phases, one liquid, one vapor. And then here, if we are talking about binary ideal mixture, then we have two component, right? So the degree of freedom is going to be 2. And then if you think about variables, you will have PT, X1, X2, Y1, Y2, right? So now this means if 2 of these are fixed, the other 4 should be fixed too. So you only really need to know 2 of these in order to calculate the rest of them, okay? So how to calculate them? So this is actually, you need to use Raoult's law, right? So Raoult's law, previously Yi, Xi, Pi, saturation. So you apply this equation to species 1, and then you apply this equation to species 2, and then you know X1 plus X2 has to be equal to 1 because it's a binary mixture. Y1 plus Y2 is equal to 1 for a binary mixture, right? So now P1 saturation, you can use Antonian equation if you know species 1. And P2 saturation, you can use Antonian equation as well if you know these constants, right? These constants you can look up in the appendix table B2, okay? And then once you know temperature, let's say if you know temperature, you can know PI saturation, right? And then if you know the system pressure, right? Basically, you have 4 equations. You already know 2 of them, so you should be able to calculate the rest, right? So that's how you figure out these thermodynamic properties using Raoult's law for a system that is experienced, that is in the liquid vapor equilibrium for a binary ideal mixture, okay? So for example, these are just like the Antonian equation, ABC constants for different type of species, right? Just for your information. All right, so now we have done, we have dealt with ideal mixture for now. But what about real mixture, right? Real gas mixture, real liquid solution. For real gas mixture, real solution, or real gases, pure gases, we actually need to introduce fugacity. Fugacity is more like effective pressure. We are going to define you later. But to motivate the introduction of fugacity, we start from this ideal gas, pure ideal gas first, right? So let's say it's a constant temperature process, dG is equal to VdP. And then for ideal gas I, dGi is going to be RT, d natural log P, because V is equal to RT divided by V, okay? And then if you integrate from a reference state, right, then dGi0, digig is going to be RT natural log P, 0, P, d natural log P. Okay, so you pick a reference pressure, usually 1 atm. Okay, and then what you will get is that GIIG is going to be just equal to GI0T. This is basically this specific or molar Gibbs free energy of pure species I at the reference state. Basically, it's arbitrary temperature but fixed P0, the reference pressure, okay? So as long as you know T, this should be a constant value, right? And then you need to have plus RT natural log P, right? So you have like the pressure dependence here. So in the end, GIIG is going to be some constant plus RT natural log P, okay? And then for pure ideal gas I, right? So GIIGTP is going to be for pure gas, right? The partial Gibbs free energy is going to be just equal to Gibbs free energy because you only have one species, right? So Gibbs free energy equal to its chemical potential is just equal to RT natural log P plus some T function, right? So it depends on pressure, right? This is like how you correlate chemical potential with pressure of a pure ideal gas, right? Now, starting from this equation, right? Like I said, right, for ideal gas, we know we just like put P in this equation. We have like some, T function and RT natural log P. That's for your how you calculate the ideal gas chemical potential, okay, or Gibbs free energy. But for real gas, right, we actually just like, because the real gas will deviate from the ideal gas behavior, right, we will just like for simplicity, we can actually use analogous equation. So here, the Gibbs free energy of your real gas or the chemical potential of your pure real gas is going to be just RT natural log Fi. Fi is called defined as fugacity of your species R. Okay. And then this fugacity is similar to the pressure for ideal pure ideal gas, but now Fi is just like the fugacity of pure real gas I. So it has the same unit as the pressure. But you can think of Fi as an effective pressure of this real gas. Okay, and then basically this fugacity is going to be a function of temperature and pressure of this system. Okay. All right, so for Fi, by definition, the fugacity of your ideal gas is just equal to its pressure, right? And then for real gas mixture, you can actually calculate its the partial molar Gibbs free energy or the chemical potential of your species I using a similar equation. Just like here, you have like fugacity of your species I in the gas mixture. Okay, and then by definition, this FIIG, right, basically in the ideal gas state, it's just equal to effective, it's equal to its partial pressure. So this Fi bar hat can be think of like effective partial pressure, right? So these are for gas. But for pure liquid, real liquid, you can also do the same thing, right? GIL is equal to mu IL is equal to RT natural log Fi. Again, Fi is kind of like an effective pressure of your liquid, right? Or fugacity of your liquid. Again, it's a function of T and P similar to this, okay? Now for pure liquid solution, right, you can use the same definition Fi hat. And then here, mu I is natural log Fi hat plus lambda IT, okay? And then by definition, we will show you FIID in the ideal solution state is going to be just equal to Xi Fi. Fi is here, okay? Xi is the molar fraction of the species I in the mixture, okay? All right, so now we want to calculate this residue property because for real gas, we know it's deviating from the ideal gas state, right? We actually want to quantify this deviation, right? So for pure gas I, GI residue property of your gas is just equal to GIRG real gas minus ideal gas. For real gas, we already know it's like, effective pressure, right? And then ideal gas is pressure. And then you plug into this equation. In the end, you will get the residue Gibbs free energy is going to be equal to T natural log Fi divided by P. And then we can actually define this as the fugacity coefficient Phi. Pi is equal to Fi divided by P, okay? fugacity coefficient of pure gas I. And then if you look at this equation, right, natural log VI is going to be equal to GIR divided by RT, okay? All right, so when P goes to 0, the system behaves like an ideal gas, so GIR is equal to 0. If this goes to 0, then VI goes back to 1, okay? This is for pure gas. And then for gas mixture, right, GIR is basically the residue partial molar property is going to be partial molar property real gas minus ideal gas. From previous slide, we already know ideal gas is YIP plus lambda I, and then real gas is FI hat. And then if you plug in, you can also define a similar fugacity coefficient of gas I in the mixture. Instead of VI, we have VI hat. VI hat is defined as FI hat divided by partial pressure YIP. And then you can see natural log if VI hat is going to be GI bar R divided by RT. And again, similarly, when you go to low pressure, you don't have like deviation from ideal state. And then your VI hat is going to be goes to 1, okay? So all these two equations, what you can see is that the natural logarithm of the fugacity coefficient of a species in the gas mixture is a partial property with respect to GIR divided by RT, right? So this is the meaning of this equation. Now, the reason why we want to have this equation is that we can actually use this to calculate your fugacity coefficient, right? So GIR, we already know how to calculate. GIR bar, we also know how to calculate. Okay, so here, for pure gas, right, natural phi is GIR, right? GIR from previous lecture, we already know, right? GIR is just integral from 0 to P, Z minus 1 dP divided by P. So you can actually calculate this integral, and then, or you can just like, because Z is going to be equal to Z0 plus Z1, so you will have natural log phi 0, natural log phi 1. So same thing, you can look these values up in the table and you plug in and you can calculate natural log phi. Once you calculate phi, you can calculate Fi, okay? For gas mixtures, similar thing, right? You will have natural log phi hat is equal to Zi bar minus 1, and then Zi is basically the partial derivative. And then for Z, again, Z is equal to 1 plus BP divided by RT if you are following a simplified virial equation of state. And then this B value is going to be complex, containing some molar fraction information in this particular case. And then you plug in and then you take partial derivative. It's complicated math, but skipping that math, what you will get is natural log phi 1 hat is equal to this. Natural log phi 2 hat is equal to this, right? As long as you know the molar fraction, as long as you know these constants, as long as you know temperature and pressure, you can calculate these fugacity coefficient. And then you can go plug back into the previous equation, right? So once you have like fugacity coefficient, right, you will understand the system properties, okay? All right, so that's for a gas state, right? For liquid solution state, in terms of like fugacity coefficient, we actually need to define activity and activity coefficient, right? Here is the basis. For ideal solution, we already give you this equation in the previous slide. And then for G of pure species I at TP, GIL is give this fugacity, right? And then basically we just like, plug this into this equation. So mu I ID is equal to RT natural log XI Fi plus lambda I T. Okay, so this is the chemical potential of species I in the ideal solution state, right? Now for a real solution, you can actually write the analogous equation defining fugacity, right? So basically mu I is equal to natural log Fi. So we give you this equation already. And then we can actually define activity. Activity is equal to Fi hat divided by Fi. And then activity coefficient gamma I is equal to AI activity divided by Xi. So basically Fi hat normalized to Xi Fi, right? So here, the activity coefficient is analogous to Phi for gas, but we use activity coefficient to differentiate between gas and liquid, okay? And then by definition, right, if your real solution recover ideal solution behavior, you know your Fi hat is going to be just equal to Xi Fi, or your Ri ideal solution state is just equal to 1, right? So here goes to 1, okay? Recover the ideal solution behavior, okay? So now basically the deviation from the ideal solution behavior for your real solution is quantified by access properties, right? So access property is similar to the residue property for gas, but we use access property to differentiate, okay? And then basically M access is going to be M minus real minus MID solution, right? And then, for example, the Gibbs free energy GI access, partial molar Gibbs free energy access is going to be GI real minus GI ideal, right? GI real is going to be mu I, like this is partial molar properties, so basically corresponding to chemical potential real minus chemical potential in the ideal state, right? So for chemical potential ideal, we already know is equal to Xi Fi, but for actual is effective pressure, right? Fugacity hat. And then you plug this back in and you will quickly realize the access property, the access Gibbs free, molar Gibbs free energy is just equal to RT natural log gamma I, right? Analogous to that Phi in the previous for residue G. And then in the end, right, GI access is going to be RT natural log gamma I, or alternatively, natural log gamma I is equal to access Gibbs free energy, molar Gibbs free energy, partial molar Gibbs free energy divided by RT, okay? So now I'm going to skip a few math, but basically gamma I, you can actually use different types of equation to calculate gamma I, okay? So one type of equation is called Magus equations. So natural log gamma I, as long as you know the molar fraction, as long as you know A12 and A21, these are constants, you plug in, you calculate these natural log gamma 1, natural log gamma 2. Okay, for binary mixture. You can also use Vela equation. So here, these are all constants again, but these are all smaller fractions. And then you can also use Wilson equation. Wilson equation is more complicated because you will have some temperature dependence here. So here, hat 1, 2, or hat 2, 1 is actually has some temperature dependence on it. But overall, these are all the equations that you can use to calculate gamma 1, gamma 2, if you are talking about a binary mixture, okay? All right. So finally, when we talked about the vapor-liquid equilibrium for a real mixture, we need to use fugacity, right? And instead of like the involving just like ideal pressure, right? But here for at equilibrium T, we know the chemical potential has to be the same, right? So basically this has to be true. And then later the chemical potential will be translated to basically essentially the fugacity of species I in the mixture in the alpha phase. is going to be equal to the fugacity elsewhere, okay, in other phases. And then fugacity in the vapor phase, we already know how to calculate that is Vi hat, partial pressure YIP. So this is ideal state, and this is the deviation from the ideal state, right? So this is the real. And then the fugacity of your I species in the liquid is again gamma I times xi fi. So here is ideal state, and this is the deviation. So basically, this is the real. And then you have to be equal for vapor liquid equilibrium. So you combine these, and then you will get this final equation: Vi hat YIP. This is the gas side, and then gamma I xi fi. This is the liquid side. Okay, so this is vapor liquid at equilibrium. Okay. And then for Fi, basically it's a function of temperature and pressure. You can actually use this equation to calculate, right, PI saturation. You can look them up. Vi saturation, you can combine with Vi later. But here, these are all values that you can look up. As long as you know TMP, you can figure out the Fi function, right? And then, like I said, you can move this to combine with this Vi hat. So basically, you combine with a capital Vi, and then move this to the other side. So YIP capital Vi is equal to gamma I xi PI saturation. So you move remain PI saturation here, but move everything else to the other side. Okay, so capital Vi. Now, for ideal solution and ideal vapor, meaning that if you have low pressure, gamma I is equal to 1, capital Vi is equal to 1. So in the end, this real solution equation, this is like the general equation, right? General equation correlating your molar fraction in gas, molar fraction in liquid, pressure, system pressure, saturation pressure of species I, and gamma I and Vi actually reduced to the Raoult's law for your ideal mixture, right? Ideal liquid solution gas mixture equilibrium, because our gamma I equal to 1, capital Vi equal to 1, okay? And gamma I, you already know how to calculate for real solution. Okay. All right. So that's a lot of content in this lecture. Hopefully you can go back to read these lecture slides a few more times to fully digest the material. But hopefully we introduce you how to analyze the phase equilibrium. We talked about phase rule, phase diagram, Raoult's law, ideal and non-ideal mixture, and then we introduce fugacity to describe non-ideal mixture. And then excess Gibbs free energy is related to that deviation, right? And then we apply all these knowledge to analyze the vapor liquid equilibrium of these mixtures, right? So that's it for today. Again, we will come back to the final lecture on chemical reaction, okay, in lecture 5. All right, thank you.